Today we're going to look at section 3.1, prime and composite numbers. Before we get to that though, we need to look at some important sets of numbers. First set we're talking about is the counting numbers. They're commonly referred to as natural numbers. This is the set of the numbers 1, 2, 3, 4, and on, and is denoted with this symbol here, kind of like a double slash N. Another set of numbers is the integers. These integers are natural numbers along with zero and the negatives of the natural numbers. This set will often be written as, well, in this form here. And we denote this with kind of a double looking Z. Now notice that N is a proper subset of Z. All the ideas of this section apply to the natural numbers, while only some apply to all the integers. So first thing we're going to talk about is divisibility. Divisibility is when the integer n is divisible by m. If n can be written as m times some other integer, equivalently, there is no remainder when n is divided by m. So, determine if 54 is divided by 9, divisible by 9. Well, what is 54 divided by 9? 6, with no remainder. So, yes. So, there are some little tricks to determine visibility. Particularly for numbers divisible by 2, 3, 4, 5, 6, 9, 10, and 12. Each of them has an easy to identify feature or rule that indicates the divisibility by those numbers, and here is a table. So, a number is divisible by 2 if the last digit is even. To determine if a number is divisible by 3, add the digits of the number together. If the sum is divisible by 3, then so is the original number. To test for divisibility by 4, look at the last two digits. If this number is divisible by 4, so is the original number. To test for divisibility by 5, look at the last digit, only the last digit. If it's a 5 or a 0, then the original number is divisible by 5. 6, if the number passes the rule for divisibility by 2 and for 3, then the number is divisible by 6, which makes sense. To test for divisibility by 9, add the digit to the number together. If that number is divisible by 9, then so is the original number. Divisibility by 10, look at only the last digit. If it's a 0, then the original number is divisible by 10. And for 12, if the number passes the rule for 3 and 4, the number is divisible by 12. So, using divisibility rules, is 45,730 divisible by 5? Looking at the last digit, it's 0. So, yes. Using divisibility rules, determine if 342,887 is divisible by 9. In this case, we add the digits, 3 plus 4 plus 2 plus 8 plus 8 plus 7. And what do we get? 7, 9, 17, 20. Excuse me. 7, 9, 17, 25, 32. 32 is not divisible by 9. So that tells us that 342,887 is not divisible by 9. Okay? So can 43,568 pieces of mail be separated in 6 bins of the same number of pieces per bin. So in other words, it's 43,568 divisible by 6. Well, is it divisible by 2? Yes. Yes for 2. Is it divisible by 3? 4 plus 3 plus 5 plus 6 plus 8, 12, 18 equals 26, which is not divisible by 3. So no. Using divisibility rules, determine if 87,762 is divisible by 10. Last digit is a 2, which is not a 0, so no. Using divisibility rules, determine if 43,568 is divisible by 4. Look at the last 2 digits. Is that divisible by 4? 68 divided by 4, and I get 117. So yes. So next we come up with what is called composite numbers. Sometimes a natural number has only 2 unique divisors, one in itself. These numbers are called prime numbers. Other natural numbers have more than 2 unique divisors. These numbers are called composite. Okay, so determine if 1,429 is prime or composite. Essentially, what we can do is go down our list. Is it divisible by 2? No. Is it divisible by 3? 1 plus 4 is 5, plus 2 is 7, plus 9 is 16, which is not divisible by 3, not divisible by 4, or 9, which is just 3 times 3. So now let's look. So we have 1,429. A lot of this is just trial and error. That's about 7. No. If it's not 2, it's not going to be 8 or 9 or 10. How about 11? Nope, not even. 12, it's not 2, it won't be 12. How about 13? Nope. 14 is a multiple of 2. 15 is a multiple of 3 and 5. No. 16, how about 17? Nope. How about 19? We can basically skip any even numbers because if 2's not in it, any even number will not work. And then likewise, we can skip 21 because it's 3 times 7 and neither of those were in it. So we go to 23. Nope. 24, 25, 26, 27. How about 29? And all I'm doing is testing to see if it comes out even. How about 31? Nope. Be 32's even, 33 goes by 3, 34, 35, 6, how about 37? Okay, and the last one we'll try is 39. No, 39 is not. So when I did 1429 divided by 37, and I did every other number before that, I get an odd amount like this, or a decimal part. It looks like a repeating decimal. So now, I tried 37, it didn't work. I got a decimal. I got a solution with decimals. So it's not divisible by 37. Now, any number over 37, 38 is not going to work because it's 2 times 19. 39 is not going to work because it's 3 times 13. So at this point, I've gone all the way up to 37. If I go beyond that, the other side of the number is going to be below 37. So it would be something I already tried if it was there. So in this case, this is a prime number. Okay, let's look at our 859. Okay, it's not divisible by 2. 13 plus 9 is 22, not divisible by 3 or 4 or 5. So then we check 7 because 6 is multiple of 2 and 3. So it's not divisible by 2, it's not divisible by 6. So we go to 7. No, 8, 9, 10. How about 11? Nope, 12. How about 13? And I am literally just dividing by each of these numbers. 14, 15, 16. How about 17? 18. How about 19? 20, 21. How about 23? 859, 23. Nope. 29. Okay, when I do 29, I get 29.62068966. So what this is telling me, if I try a number that's greater than 29 here, I'm going to get a number less than 29 here. So now I'm just doing the opposite of what I've been doing. So this also is a prime number. Okay. Well, how about 5,067,322? 2. So this one is a composite. It doesn't say to break it down, so that's all we'll do. Composite number is divisible by 2. So 2 times something will give me that number. It's composite. Okay, let's look at our next one here. 1,477. I can see it already. 1477 divided by 7 is going to be 211. It's not divisible by 2. 5 and 14 is 19 or 3. So it's not 4, not 5. Won't be 6. So we take 7 and we get that. So we know it is a composite number. The next thing we're looking at is finding the prime factorization of composite numbers. We want to break them down of numbers. Defining the prime factorization of a composite number means writing a number as the product of all of its prime factors. For example, 80 would be 2 times 2 times 2 times 2 times 5. Notice that all numbers being multiplied on the right-hand side are prime numbers. Sometimes prime numbers repeat themselves in the factorization, and when this happens, we can write the prime factorization using exponents. So we could write it as 80 equals 2 to the fourth times 5, where 2 is raised to the fourth power. 4 is the exponent and 2 is the base. Well, generally in the exponent notation, a to the b, the number represented by a is the base, and the number represented by b is the exponent. So you might wonder if finding the prime factorization can result in a different factorization. The fundamental theorem of arithmetic tells us that there's only one prime factorization for all given natural numbers. So every natural number other than 1 can be expressed in exactly one way apart from arrangement as a product of primes. So they might be in different order, but the reality is it's the same thing. So find the prime factorization of 90. Well, we can do this like this with a take 90 and it's 2 times 45. And 45 is 3 times 15. 15 is 3 times 5. So I have 2 times 3 times 3 times 5. That's it. All those numbers are prime. Okay, what about 85? Let's see. I don't see a 2 or a 3 in there or a 4, but I see 5 times 17. So that's it. 5 times 17. How about 280? Well, 280. You have 2 and 140. I have 2 and 70. I have 2 and 35. I have 5 and 7. So I have 2 times 2 times 2 times 5 times 7. There's only one prime factor of 180. So this question is find the number of different prime factors of 80. Okay, it's not asking factorization, it's asking to find factors. So we still need to find it. 180, 2 and 90, 2 and 45, 3 and 15, 3 and 5. So the factors, we have 2 squared times 3 squared times 5. So 2, 3, and 5 are the prime factors of 180. So now we do something called finding the greatest common divisor. Two numbers often have more than one divisor in common. All pairs of natural numbers have the common divisor 1. When divisors, it's often the case that the largest is of interest. This divisor is called the greatest common divisor and is denoted GCD. It's also sometimes referred to as a greatest common factor. To find the greatest common divisor of 270 by listing all divisors of each. So our 99, we got 3 times 3 times 11. 270, we got 3 times 3 gives me 9 times 3 again times 2 times 5. So what we look at is how many of these factors, what's the most of these factors they have in common. 99 has 2 3s in it. So does 270. So the greatest common divisor is 3 times 3 or 9. Using prime factorization, determine the greatest common divisor of 36 and 128. I have 36, which is 2 times 18, which is 2 times 9, which is 3 times 3. 128, we have 2 times 64 times 2 times 32 times 2 times 16 times 2 times 8, 2 times 4, 2 times 2. 4, 8, 16, 32, 64. So what do they have in common? Well, there's two twos here and there's more than two here. So our greatest common divisor would be 2 times 2 or 4. Again, using prime factorization, determine the greatest common divisor of 120 and 200. 120, I have 2 times 60, which is 2 times 30, is 2 times 15, which is 3 times 5. For 200, I have 2 times 100, is 2 times 50, 2 times 25, which is 5 times 5. So now I have 3 2's and a 5. So my greatest common divisor is 2 times 2 times 2 times 5, which would be 40. So what are the applications of this? What purpose does this serve? The greatest common divisor has uses that are related to other mathematics, such as reducing fractions, but also in everyday applications. You were designing a brick patio made of squares 5 centimeters thick, but you need to determine the width and length of those bricks. The patio will be 400 centimeters by 540 centimeters. What's the largest size square or divisor between 400 and 540? So at 400, we can break it down to 2 times 2 times 2 again. First 2 brings it down to 200, then 100, then to 50, and to 25, 5 times 5. And 540, and look at 2 times 270, which is 2 times 135, which is 3 times 45, which is 3 times 15, which is 3 times 5. So I have 2 2's, and I have a 1 5. So 2 times 2 times 5, which is 20 centimeters. So we can use a 20 by 20 square and it will fit. It will be 20 this way and 27 that way. Okay. There are 3 gym classes. The number of students in the classes is 21, 35, and 28. What is the largest team size that can be formed if teams from every class must have the same number of students? So again, we're looking for the greatest common divisor. Well, 21 is what? 3 times 7? 35 is 5 times 7. And this is 2 times 2 times 7. Looks like the only number they have in common is 7, so we need 7 people teams. And there'll be 3 here, 5 there, and 4 there. Okay. Next, we talk about what's called a least common multiple. This is the flip side to a divisor of a number, is the multiple of the number. For example, 5 is the divisor of 45, and so 40 is multiple of 5. More generally, if the number A divides number B, then B is a multiple of A. This drives the idea of the least common multiple of a set of numbers. Common multiple of a set of numbers is a multiple of each of those numbers. For instance, 45 is a common multiple of 9 and 5 because 45 is a multiple of 9. 9 is 45. And 45 is also a multiple of 5 because 5 divides by 45. The least common multiple, or LCM, of a set of numbers is the smallest positive common multiple of that set of numbers. One way to find the LCM of a set of numbers is to create a list of multiples of each numbers in the set and then identify the smallest multiple that appears in those lists. So we start with 12, 24, 36, 48, 60, right? And 15, we have 15, 30, 45, and 60. So 60 is the LCM. That's how we do that. Another method we can use to find the least common multiple is to find the prime factorization of the number in the set to build the least common multiple of the numbers based on the prime divisor of the numbers. The LCM can be built from prime factorization of the numbers in a set in a similar way as when finding the greatest common divisor. Here's the steps. So we'll start with find the prime factorization of each number. Identify each prime that is present in any of the prime factorizations. Identify the largest exponent of each prime identified in step 2 and multiply the prime factors identified in step 2 raised to the powers identified in step 3. So we're going to find a prime factorization of 20 here, which is 2 times 5. And then we're going to find a prime factorization of 28, which is 2 times 7. Now, what this means, this is 2 to the second power times 5, 2 to the second power times 7. So, I consider this 2 to the second power. I'm going to write it out this way, and you'll see why in a moment. And this 5 here. Now, I look here, and I've already have taken care of 2 to the second power. So then I just need to add this 7. And if I multiply this all out, I have 140 is my least common multiple. Takes a little practice, but it's not real difficult. So again, let's use prime factorization on 150, 240, and 462. Starting with 150, that's 2 times 75, which is 3 times 25, which is 5 times 5. Going with 240, we have 2 times 120, which is 2 times 60, which is 2 times 30, which is 2 times 15, which is 3 times 5. Okay? Here I have 2 times 231, 3 times, let me think about that one. 231 divided by 3, 77. So that is 7 times 11. All right, so we start with 150. I have 2 times 3 times 5 times 5. Okay? So I have a 2, I have a 3, and I have a 5. I need 3 more 2s. 1, 2, 3. So I have a 2, I have a 3, and then I need a 7 and an 11. And then we just multiply it all out. 2 times 3 times 5 times 5 times 2 times 2 times 2 times 7 times 11. And I get 92,400. And that's how that works. Let's look at another one here. I have 18, 24, and 40. Well, 18 is 2 times 9, which is 3 times 3. 24 is 2 times 12, which is 2 times 6, which is 2 times 3. 40 is 2 times 20, is 2 times 10, which is 2 times 5. So look in here, I can take all of these. 2 times 3 times 3. I have 1, 2, and I have 3, so I need 2 more 2's. 2 times 2. Now I already have 3 2's. 1, 2, 3, but I don't have a 5. Then I multiply it all out. 2 times 3 times 3 times 2 times 2 times 5. Oops. And I get 360. Now you could check this too. What is 360 divided by 18? Well, it's 20, so it works out even. And 360 divided by 24, well, that's 15, and it works out even. And 316 divided by 40, well, that's 9, so it works out even. So this is what I'm looking for. So let's talk about applications. Some applications of the least common multiple involve events that repeat at fixed intervals, such as visits to a location. Other applications involve getting things to be of equal magnitude using parts that are different sizes. In each case, we may be looking to determine when two processes line up. So, the Sun, Venus, and Jupiter all line up on a given day. Venus orbits the Sun once every 255 days. Jupiter orbits the Sun every 4,330 days. We won't worry about decimal values of the days. How many days will it be until they line up? So I'm looking for the least common multiple again. So this could get a little long. So I have 255, or maybe not. 5 goes into that, right? Times 51, which is 3 times 17. Now let's look at this 4,330. Now 2 goes into that. I'm going to use my calculator here, leaving me with 2165. Okay, 3 does not go into that. 4 does not, but 5 does. Leaving me 433. And I don't think anything else goes into that. Oh, 433. Not 3, not 2, not 5, not 10. Let's try some of the odd numbers in there and see. 433 divided by 7, nope. 433 divided by 11, nope. 433 divided by 13, nope. 433 divided by 17. And as you do this more and more, you'll realize what numbers you need to look at. They're the prime numbers. 433 divided by 19, nope. And that gets me to where I need to be to show that it's not going to have any further factorization. So I take this 5 and 3 and 17. Now this 5 is accounted for, so I take a 2 and I take a 433. So we take 5 times 3 times 17 times 2 times 433, and we get 220,830 days. So Venus and Jupiter line up with the Sun every 220,830 days. Just out of curiosity, roughly every 600 years. Okay, so last one for this section. In an internet giveaway, every 130th person who submits a survey receives $250, and every 900th person receives a free cell phone. How many submissions must be received for the first person to receive both prizes? So again, do our prime factorization. This is 2 times 65, which is 5 times 13. 900, 2 times 450, 2 times 225, 3 times 75, 3 times 25, 5 times 5. So I take the 2 and the 5 and the 13 from 130. That accounts for a 2 and a 5. So I have another 2. You have 3 more 3s, and I have 1 more 5. Now multiply them out. 2 times 5 times 13 times 2 times 3 times 3 times 5. And get 11,700 customers. It would be the first one to get both. So that finishes up sections 3.1.